Hi, I'm Gregory from the University of Gothenburg and Chalmers to present some work on the impact of solver choice on model-based test generation. Now, a common form of model-based test generation is based on the use of bounded model checking, where properties expected of the model are embedded as Boolean predicates describing states encountered during execution paths. Model checking relies on the use of an SMT solver. Solvers explore the state space of the model in search of states that violate the specified properties by casting these property violations as a Boolean satisfiability problem. We seek values for the input variables of the model that lead to a state violating those properties. If the model checker finds a violation, it produces a counterexample, a partial test specification demonstrating that violation. Often we embed properties we want to show that can be met by the model. We negate those properties, claiming they cannot be met. The model checker then attempts to produce a counterexample illustrating how the property can actually be met. This counterexample offers test input that can be applied to the real system or the model to demonstrate that it can show a property of interest. Now, many different SMT solvers exist, and in many cases you can actually choose among several for test case generation. Once upon a time, this wasn't the case. Each follows their own algorithm, each may produce differing counterexamples. Some are better suited to some problems than others. But with advances in computing power and algorithm design, we increasingly encounter situations where multiple solvers can produce test cases for a given model. If each is able to handle similar model structures and data types, doesn't matter which one we use. To investigate this, we performed an experiment. We first gathered case examples, a set of 37 software models written in the Loost data flow language. We studied models with varying mixtures of Boolean and numeric data types. We generated faults. We seeded up to 500 false mutations in each model. We then used 4 different solvers, each using their own algorithms and supporting different underlying theories: Z3, MAFSAT5, CVC4, and Yikes2. All 4 should be able to handle the types of models we studied, allowing us to compare results in a fair manner. Now, different sources of testing goals will impose different constraints on the test suites, and so we look at 4 criteria based on structural coverage of Boolean expressions: branch coverage, decision, condition, and MCDC, in order of complexity. We then compute the effectiveness of the resulting test suites. We look at whether the solvers are able to satisfy the full set of testing goals, and we look at the number of faults discovered by each test suite for each model. In checking the behavior of the model, we need a test oracle. The oracle specifies expected values for a set of variables, so we vary the size of that set. We use what's called an output-only oracle, looking at the behavior of the output variables. This is our standard practice. We also look at a maximally powerful oracle that checks the expected values of all internal and output variables. This is less realistic, but gives us an upper ceiling on fault detection for these test suites. Our first research question looks at the solvers in terms of their basic ability to generate test cases. Are there models where certain solvers cannot satisfy the full set of goals? Well, what we see is that Z3 and Yikes2 achieve full satisfaction over all 37 models, while CVC4 and MAFSAT5 fall short on a subset of those of 7 of the models. In this experiment, we provided all solvers with the same timeout, either 72,000 seconds or a path with a length of over 500 transitions per test goal. Both limits are well over what's generally required, and so these timeouts imply that the solvers would never find a solution regardless of what we set the timeout to. Now, our remaining research questions examine the impact of solver choice on fault detection of the generated test suites. There are 18 of the 37 models where we see performance differences between the solvers across all 4 coverage criteria. Essentially, what we see is that for the output-only oracle, CVC4 and MAFSAT5 outperform the Z3 solver with significance. With the maximum oracle, CVC4 and MAFSAT5 outperform both Z3 and Yikes2 with significance, so we do see clear performance differences between these solvers. Now, our goal is not to recommend one single solver. Rather, we want to make recommendations for solver improvement across the board. We've examined the impact of several factors, the first of those being the test oracle we use. We use two test oracles here. The output-only oracle reflects the standard practice where we check program output and see if it reveals a fault. And then we have the maximum oracle, which reflects the situation where we specify expected values for all internal and output variables of the model. As I said before, this is not a realistic oracle. In practice, it would require a lot of work on the part of the tester. However, it's great for looking at the best case performance, and in this case, it is useful for understanding a critical feature of solver performance, the ability of the solver to choose input that both triggers faults and propagates the corrupted state to the model output. There is a clear performance gap between the two oracle types. This indicates that some faults are triggered, but corrupted state is not propagated to the output level. Rather than suggesting a difference between the four solvers, this identifies an area of improvement for both future solvers and test generators. Solvers and test generation frameworks could improve fault detection by factoring effect propagation into input selection. Ensuring propagation output is clearly important and could be addressed by explicitly factoring path constraints requiring observability, a non-masking path from variable assignment to output into the constraints being solved. Now, all four of the sources of testing goals used in the study are structural coverage criteria based on Boolean expressions. Coverage criterion does influence the resulting fault detection. MCDC satisfying suites tend to detect more faults than those for the other criteria, but that rise occurs regardless of the chosen solver. However, from the results for MCDC, we can also see there is some relation between solver performance and the source of testing goals. For branch, condition, and decision coverage, there are clear performance differences between solvers. For MCDC, performance is actually quite similar across all the solvers. MCDC is the strictest of these criteria. It imposes the most constraints on the input we use, so it follows the solver would have less freedom to choose input that meets its goals, narrowing that performance gap. Simple goals can be satisfied with a wide range of input, magnifying the differences. The choice of testing goals is up to the developer, but as solvers increase in efficiency and their ability to solve complex constraints, it becomes easier for the developers to make use of stronger criteria like MCDC as a baseline approach rather than weaker criteria like branch coverage. Now, like in standard programs, model variables have data types. We looked at Boolean and integers specifically in the models in this experiment. And how those data types are handled is going to differ greatly between solvers, and much of the performance gap may come down to how solvers choose input variables. The models where test suites differ in performance tend to have numeric input variables. CVC4 and MAFSAT5 choose a far wider range of values for those variables, leading to improved performance. We observe a similar phenomenon for Boolean variables at times, where Z3 outperforms the other solvers. And in those rare situations, we saw that Z3 sets Boolean variables to true more often than the other solvers would prefer false values. That effect is more muted with numeric variables, but still, by trying a wider range of values, Z3 generated better test suites in that situation. Solvers could improve fault detection by applying a wider range of values to variables rather than tending toward fixed values. The counterexamples being produced are a partial test specification. The solver will only provide values for input variables that directly impact the execution path. That's a deliberate design decisions. Solvers can simplify the state space by dropping unnecessary variables. If a value is not provided, the test generation framework itself needs to fill something in. And that will often be a default value, like 0 or false. And as we saw, constantly using the same values tends to decrease the probability of exposing faults. The strategy used by the test generation framework to fill those gaps is going to also impact fault detection. And the test generation framework could, for example, apply random values instead of a static default. Now, to avoid bias in our experiments, we used the same settings regardless of the solver employed. However, every solver offers a number of parameters that could be used to tune the search. As has been seen time and time again, general solutions can be outperformed by solutions tuned to the particular problem, and by tuning the parameters used by the solver to control its search strategy, we may see vast improvements in performance. Automated approaches to parameter tuning have been proposed in multiple domains, generally making use of some form of reinforcement learning, and those can be used to tune test generation automatically. Now, I know this was a very short talk, so I'd recommend checking out the paper, but for now, I would welcome any questions at either here or in greg@greggay.com,